Hey everyone, and welcome back to the Deep Dive. Today we're going to do a deep dive into a research paper that you sent our way, all about something called distillation scaling laws.
Sounds pretty intense.
Yeah, and to make it even more intense, it's all about making large language models, or LLMs, for short, more efficient. And that is a huge GE topic right now.
It is, and it's an area of research that's just exploding with new findings,
Uh,
and this paper that we're going to deep dive into today is a great example of that. It's really interesting stuff.
I'm excited to get into it, but before we do, let's just take a step back for a sec. For those of our listeners who aren't living and breathing AI research every day, can you give us a quick breakdown of what LLMs are, why everyone's so excited about them, why are they so important?
Sure. So an LLM, or a large language model, is basically like a super-powered chatbot. It's been trained on an unbelievable amount of text data, and it can do all sorts of cool things like, it can translate languages, write different kinds of creative content, and even answer your questions in an informative way, even if they're open-ended, challenging, or
It's
strange.
like, it's like the ultimate writing assistant that we all wish we had, but with so much more potential. But
Exactly.
I've heard that training these LLMs can
Yeah.
be pretty resource intensive. Is that where the efficiency part comes in?
That's exactly right. Training these massive models takes an incredible amount of computing power
Yeah.
and, energy, which can be very expensive and also have a big environmental impact. And, if we want to run these LLMs on everyday devices like, your phone or your laptop, we got to figure out how to make them way more efficient.
Okay, that makes sense. So where does this research paper we're diving into fit into all of this?
Well, this paper looks at something called scaling laws to try and figure out how to make distillation more efficient.
Okay, wait, hold on. Scaling laws. What is that? Like some rule book for building AI?
That's actually a pretty good way to put it. So scaling laws are basically relationships between the size of an LLM, the amount of data it's trained on, how much computing power is used to train it, and then ultimately how well it actually performs.
Okay, so are you saying that, like, if researchers can understand these relationships, they can figure out how to build, like, the most powerful AI, but using the fewest resources?
That's exactly it. It's all about optimizing the entire process. And, this paper, they're specifically looking at how scaling laws apply to something called distillation.
Okay, we're getting into the nitty-gritty now. Can you explain what distillation is?
So imagine you have this big, highly trained LLM. We call it the teacher model. Okay.
Gotcha.
Distillation is basically the process of taking all the knowledge from that teacher model and transferring it to a smaller one, a more efficient student model.
Oh, okay. So the student model is basically learning from the best of the best. But then why not just use that teacher model directly? If it's so powerful, why even bother with the student?
Well, like we talked about, running these massive models can be insanely resource intensive. So distillation basically allows us to kind of create these smaller models that can perform almost as well as those big ones, but they use way less computing power and energy.
Okay, I'm starting to get it. So how does this knowledge transfer actually happen? Does the teacher, like, give the student a bunch of lectures?
Not quite lectures, but a good analogy. Basically, the teacher model generates, a bunch of outputs based on some input data.
Okay.
And then instead of training the student model directly on that original data, we train it to kind of match the teacher model's outputs. It's almost like the student is learning to mimic the teacher's expertise.
That's really interesting. But isn't there a risk that, the student will just become a copycat,
Yeah.
just kind of parroting the teacher without having any of its own unique insights? Like, how do we even know it's really learning?
That is a fantastic question, and it really gets at the heart of a lot of the ongoing debates about distillation. So while the student model does learn from the teacher, it doesn't just memorize the outputs.
Okay.
It learns kind of a more general representation of the knowledge, which allows it to apply that knowledge to new situations.
Okay, so it's not just about memorizing. It's about really understanding the underlying concepts. So tell me, what were some of the key findings of this research? Was there anything that really surprised you?
Oh, absolutely. One of the most interesting findings was that the quality of the teacher model isn't always the most important thing when it comes to how well the student model performs.
Wait, really? I would think that, a super smart teacher would always lead to a super smart student.
Yeah, you would think so, but it turns out, the world of AI doesn't always work that way.
Okay, you've got to tell me more. I'm all ears.
So the researchers actually found that using a very large, like really complex teacher model can sometimes be inefficient when it comes to distillation.
Now that is surprising. How is that possible?
Well, it seems like When the teacher model is just too big, the student model can actually have trouble absorbing all of the knowledge effectively.
Yeah.
The sheer complexity of the teacher's outputs can be just too overwhelming, which makes it hard for the student to pull out the most important information.
So it's like trying to teach, a kindergartner advanced calculus. They might pick up a few things, but they're not going to understand the whole picture.
Exactly. It seems like there's a sweet spot when it comes to the size of the teacher model. If it's too small, it won't have enough knowledge to teach, right? But if it's too big, it can actually hold the student back.
Okay, so how do you find that sweet spot? Is there some formula or something?
That's where these scaling laws come in. What the researchers did is they were able to identify these patterns that basically connect the size of the teacher model to how well the student model performs, given certain resource constraints.
Okay, so this research is basically giving us a guide to picking the right teacher for the job.
Exactly. It's about understanding the trade-offs and finding the most efficient path to creating a student model that performs really well.
This is so interesting. What other discoveries did they make?
Well, this is where things get even more interesting. They found that sometimes just using good old-fashioned supervised learning can actually be more efficient than distillation.
Hold on, I thought we were all in on this distillation thing. What's supervised learning got to do with this?
Right. So remember how we were talking about how in distillation, you're training the student model to match the teacher model's outputs?
Yeah, that was like the whole point of distillation.
Exactly. But with supervised learning, we basically just skipped that whole teacher step.
Yeah.
We train the student model directly on the original labeled data without even using a teacher model.
So it's like, learning straight from the textbook instead of getting notes from a classmate.
That's a really good analogy. And what was surprising to the researchers was that in those situations where you're only focusing on training the student model, you don't need the teacher model for anything else, supervised learning can sometimes be a more efficient way to do it.
So distillation isn't always the best way to go. That's kind of a big deal.
It is. It really challenges this idea that distillation is, always the most efficient approach. It just shows that you really have to carefully consider your resources and goals when you're setting up these AI training processes.
Man, I'm getting a real crash course in AI training today, and I'm loving it.
Mhm.
So if supervised learning can be more efficient sometimes, when does distillation really shine? Like, when is it the right tool for the job?
So one of the biggest advantages of distillation is when you want to create a bunch of different specialized student models.
Oh, okay. Tell me more about that.
So imagine you've trained this big, powerful teacher model that's, really good at a whole bunch of different things.
Yeah.
With distillation, you can take that one teacher model and use it to train a whole bunch of smaller student models, each of them kind of specializing in one specific task.
So it's like having a master chef who can train, sous chefs specializing in pastry, grilling, sauces, whatever you need. Each student model gets that, fine-tuned expertise without having to start from scratch.
Precisely. It's a much more efficient way to create this diverse set of AI models, each with its own unique set of skills.
That makes a lot of sense. Now, you mentioned something earlier called compute optimal distillation. Can you break that down for me?
Of course. Remember how we talked about how important it is to find that right size for the teacher model?
Yeah.
Not too big, not too small.
Yep, finding that Goldilocks zone.
Exactly.
Yeah.
So compute optimal distillation takes that idea even further. It's not just about finding the best teacher model size. It's about thinking about how much computing power it takes to train that teacher model in the first place.
So it's like when you're deciding what to teach the student chef, you also have to think about how much the ingredients are going to cost,
Right.
right? You want to create a dish that's both delicious and affordable.
Perfect analogy. So we might think that using the biggest, most powerful teacher model will automatically create the best student model, right?
Yeah, that makes sense.
But what if training that massive teacher model takes like a crazy amount of computing power and energy? Well, suddenly our best student isn't so efficient anymore.
It's like using a truckload of truffles to make a tiny bottle of truffle oil. Sure, it might be amazing truffle oil, but it's probably not the smartest way to use your resources.
Exactly. Compute optimal distillation is about looking at the entire process. It's about finding a balance between, how capable the teacher model is and then how much it actually costs to train that teacher. And sometimes a slightly smaller teacher that was trained in a more efficient way, that might actually be the best way to create a powerful student model overall.
Wow. This is making me realize how much thought and strategy goes into training these AI models. It's
Yeah.
definitely not as simple as I thought.
It's a really complex process with a lot of different moving parts. And this research on distillation scaling laws, this gives us some really valuable tools and insights to help us make smarter decisions about how we train and deploy these incredibly powerful AI models.
All right, so we've talked about what distillation scaling laws are, why they're important, and how they work. But let's shift gears now and talk about why this all matters. What are the real-world implications? Why should anyone who's not an AI researcher care about any of this?
You know, that's a great question, and one that I think we should definitely talk about. I think one of the most exciting things about this research is that it could lead to more people actually being able to use these powerful AI tools. Because right now, training and running these large models is really resource intensive, right? It often requires like specialized hardware. You need people who know what they're doing. It's not easy.
So you're saying it's mostly just big tech companies and research labs that have all the resources to really work with AI.
Exactly. But if we can make these models more efficient, we can start to give everyone access to these powerful technologies.
Yeah.
Imagine, being able to run these really sophisticated AI models on your smartphone or laptop without needing a supercomputer.
Okay, now that's something I can get behind. That would open up so many doors. You could have AI-powered tools for, things like language translation or writing, even things like personalized education, and it's all available to anyone with a device.
Yeah, and it's not just for personal use, right? This kind of access could completely change entire industries. Think about, healthcare workers in really remote areas. They could use AI-powered tools to diagnose patients.
Yeah.
Or think about small businesses that could use AI to, become more efficient. There's so much potential.
Wow, I never even thought about it like that. That's amazing. It's like AI is going from this exclusive club to something that can help everyone.
It really is. And besides accessibility, there's another big thing we need to talk about, the environmental impact.
Yeah, I was just thinking about that. Training these huge AI models must take a lot of energy, right?
A lot. It's a big concern. But this research is exciting because it shows us how we can actually develop AI in a way that's more sustainable.
Yeah.
If we can get the same or even better performance out of smaller, more efficient models, we can really cut down on how much energy we're using and how much carbon we're putting out there.
So it's not just about making AI better, it's about making it more responsible.
Exactly. It's about finding a balance between, really pushing the limits of what we can do while also making sure we're not hurting the planet in the process.
I love that. So it's like we're not just rushing into the future of AI. We're trying to do it the right way.
Exactly. And there's one more practical thing I want to mention, which is that this research can help save AI developers a lot of time and effort. Imagine you're trying to train a new model with distillation, but you have no idea what the best setup is. You're like, which teacher model do I use? How big should it be? How much data do I even need?
And like a lot of guesswork and a lot of wasted time and energy.
It is. But these distillation scaling laws, they give us like a roadmap, right?
Hmm.
They help developers understand, how all these things are related, model size, data, compute power, how well it works, so they can make better decisions about how to design and train their models.
So it's like having a cheat sheet for building AI, right?
Yeah, basically. It takes out some of the guesswork so developers can just focus on building the best AI models possible.
I think we've covered so much today. We've talked about what distillation scaling laws are, what this new research has found, and what it all means for the future of AI. It's clear that this is really important and could change how we build and use AI in the years to come. Any final thoughts you want to share with our listeners?
Just that the field of AI is always changing, and this research is a perfect example of how quickly things are moving.
Yeah, it's definitely an exciting time to be following this stuff.
It is. So stay curious, keep learning, and let's see what amazing things we can do with this technology.
I love that. A big thanks to our expert for breaking all of this down for us today. It's been a fascinating deep dive into distillation scaling laws. And for everyone listening, if you want to learn more, don't forget to check out the show notes where you'll find links to the research paper and other resources. And until next time, keep those brains buzzing, and we'll see you on the next deep dive.